So check out this little assembly program right here. We're going to move the value of 0 to REX, which is just a variable in the CPU. We're going to increment REX, which is going to add 1 to it. And then what I'm going to do is jump to loop, which is this little label right here. And we know jump will move the execution up to loop. So if I compile this and I step through it, you see REX is 1, and then we jump to the top and we keep on incrementing over and over and over again. And you see REX just continues to go up. So what if we didn't want jump to always jump? What if we wanted at some point for it to fail, to skip? What if we wanted it to be conditional? And that's what we're going to do in this video. We're going to add the last piece that we need to make real programs that have intelligent movement, because right now everything that we've written just always repeats the same thing over and over again. So now we're going to have essentially branching logic. By the way, I'm using the x64 playground. If you go to x64.halv.it, it will load up. You click launch the app, and then just make sure that you select GNU. That's the one that we're using. So what we want to do is put an if statement here. Let's say that we wanted REX to reach the value of 3, but not go anymore. So at this point, we wouldn't want it to jump anymore, and we would want it to just fall through. So we would ideally want to loop through until REX reaches 3, and then this should fail. To get this done, let's look at an if statement in something like C. The way that we tend to read this is if a condition is true, then we do something. But really, the way that we need to approach it with assembly is if the condition is not met, then we actually want to skip doing something. We want to jump until after the if statement. So it's a little bit backwards, I would say. Instead of having if condition and jump inside, if the condition is met, we don't really do anything. We just let the instruction pointer proceed downwards, and it will execute what's inside the if statement. But the jump occurs if the condition fails. So if we look at this in assembly, let's get rid of our loop for now, because that's just going to confuse things here, and we'll add the loop back in after. So if we move, let's say REX, let's say the value is 3, and what we want to do is say if REX is 3, then print REX is 3. This is all we want to do here. So of course, first we need to add the actual REX string. So let's do that in the data segment. Let's put S1 and put ASCII. REX is 3 exclamation mark. And then we need the length, which we put with a dot, just marks the current memory position and subtracts this memory position. We get the difference, which is the length. Let's put print here, and we'll put move REX 1, move RDI 1. Then we load our string to RSI, and we load our length to RDX. And I tend to put these in brackets. You don't really need to with the GNU, but in other assemblers you do. And so now what we want to do is check the value of REX. If it's 3, we want to jump here. And if it's not, then I guess what we'll do is we'll exit. So let's put our exit here. Exit 60, we can put 0, and we can do a syscall. And I forgot my syscall here. So if REX is 3, we print. If REX is not 3, right? This is the important part that we have to kind of come to terms with assembly. We really care if the condition is not met, because very simply, if the condition is met, we just fall to the next command. If we have our if statement right here, ASM if this is true, we do nothing. We just continue to fall through the code. But if it's not, then we'll skip to the exit, and this is that conditional jump. So let's do that. This is a new command here. We're going to compare the value that we want, which in this case it's REX, and we're going to compare it to 3. Now if we look at these registers, there are some flags down here that we haven't looked at yet. And I'm going to make a video all about the flags. But in this case, all we need to know right now is this compare command will compare any two values. And the compare is going to compare them in every way that you can all at once. So it's going to compare if it's equal. It's going to compare if it's greater than, less than, equal to. All of that happens essentially simultaneously. And then all we're going to tell the assembler is what we want to know. So what we want to know is if they're not equal, right? Because this is the inverse here. So if they're equal, which we could do if they're equal, and that command is jump if equal, but we really want to jump if it's not equal, right? We want to skip it. We want to skip the body of the if statement. So we want to jump if it's not equal to exit. So if we go through, we move 3 to REX, and then we compare, and look at down here, look at these flags when I click next. I'm going to click next right now. So we see we had some changes here. We compared REX to 3. Now the 0 flag means that they're equal, and we're going to jump, right? The next command, we're going to jump if they're not equal to exit. So in this case, they are equal. So we're going to fall through to print. And there's our message. REX is 3. Now let's change it to 4. So let's compile again and let's run through. we set REX to 4, we perform our comparison, and then now we're going to jump if they're not equal to exit. So we click step. We're jumping if not equal to exit. We skipped that print statement. This is the if condition. This is the body. This is the end if, I guess you could say. So if the condition, and here is the body, and here is the end if. And all we're doing is we're skipping the body if we fail the condition. And we can write this in many different ways. This is probably the cleanest way to do it, where we're only jumping once. You could write it, of course, where you jump to print if you wanted to, but the idiom here is that we compare and we just fall through in the condition that we want, and we skip the entire body when we want to exit. So the example that we had earlier was a loop. So how do we convert this into a loop? In this case, our body is going to change because all we want to do in the body is increment REX, right? We want to essentially recreate. Let me get rid of all this and all this. I think it's a little bit cluttered. So we have the end of our if statement here. We can leave that end of if statement. And what we want to do is start off with REX at 0. And we really want to have this, right? While REX is less than 3, we increment, right? That's all we want to do. And then afterwards, we could say that we return 0. So if we edit this for clarity, it kind of looks like this. We have a while loop. While REX is less than 3, we increment. And then at the end, we could say return 0, which is our exit 0 right here. And remember, it's a bit backwards, right? This is saying if REX is less than 3, we perform this, right? But we're not really jumping if it's a true condition. We want to jump to skip if it's a false condition. So what's the inverse of that? So we kind of have to flip it. So if we compare REX to 3, then we want to jump if greater than or equal to, and we'll jump to exit. So we compare REX to 3, and we're jumping if REX is greater than or equal to. So that means that if that fails, if it's not greater than or equal to, then it must be less than, and we fall through. And then we need to add the actual body of the statement to increment. So that would just be increment REX. And then we need to loop back to the top, which of course is going to be a jump statement. So we jump to this line of code here. And if we compile this, it's going to be an error, but I wanted to see this address because we could put this address in manually, 0x401007. We don't always need to use labels. Of course, it's much safer to use labels, but I want to demonstrate that the labels are not anything magical. It's just replacing these addresses. So if we compile this, we set REX to 0, we compare it to 3, and only if it's greater than or equal to 3 do we jump to exit. In this case, we don't jump because it's not greater than or equal to 3, it's 0. And then we're going to increment. So now we have 1 in REX, and then we jump to the start. Even though we have this manual address here, right? Very bare metal looking statement, we're just jumping to this line of code. We're repeating this line of code. We compare it again. 1 to 3 is not greater than or equal to, so we increment. Finally, we reach 3, and is it greater than or equal to? Yes, it is. So now we finally jump down to exit. We can exit our program. So we've just implemented this logic here. While REX is less than 3, then we increment. When REX finally is not less than 3, so in other words, when it's greater than or equal to 3, then we skip and we return 0. And looking at it this way, it becomes very obvious that a while loop is just an if statement with a jump. If we remove this jump here, it's a single if statement. So we increment by 1. So in this case, we just wrote if REX is less than 3, then increment. So to turn it into a loop, we just add a jump here. So we jump again back up, and I'll add a tag just to make it easy. So we have loop, and I'll just jump to loop. We compile this, and we can just step through 1, 2, and 3. So now that we're dealing with loops, I'm going to show you another command here. Let's say that we wanted to not have to go through this manually. Let's say that we wanted this to be a high value, like 255, which is FF, right? You can write this in manually, 255. So we don't really want to sit here pressing forward every time. But in the way that we wrote our program, if we just click continue, or if we run it, then in the end, REX is going to be this value here when we were exiting the program. Now we could use a different register, but I'm going to show you a command that we can use to essentially add a breakpoint to our program. Now in a real debugger, we would be using breakpoints, but we kind of have to use a little workaround here, and it's just called interrupt3, int3. And that tells the CPU, or in this case, the emulator, that we just want to break there. There's an interrupt in the CPU that it needs to handle. It's an empty interrupt, but it works perfect for our case, because now we can press continue. Oh, I put it in the wrong spot. Okay, that should be better. Now we could just press continue, and you see it stopped here at the sign of code, and FF is our RAX. So this loop ran 255 times, and it moved RAX all the way up to FF, but we're able to see it before we finish exiting the program. So wherever you want to have a breakpoint, you can add interrupt 3. This is very, very helpful when we're debugging, because if we have a piece of code that works well, but it takes a long time, we could just press continue and run through that piece of code and still pause and be able to manually go through where we want. So now let's talk about negative numbers, because we haven't really covered that yet. So first, how are negative numbers represented? And I do have a pair of videos on the binary signed or unsigned numbers. They're a bit slower, but I think they paint a decent picture for what you need to know. But if we move RAX, right, the value of -1 to it, then we'll see that it's a huge looking number. In fact, -1, when we read it as an unsigned value, it's the largest unsigned value we could have. However, when we read this in a signed mode, it's quite small, it's -1. So it just depends on what mode we're in. Are we signed? Well, that's a tiny number, -1. Are we unsigned? Well, that's a huge number, as large as you could possibly get. So because there's two ways to look at it, there's actually two sets of commands when it comes to conditional jumps. And that's how we treat the comparisons. We can treat the comparisons in signed or unsigned. So here's an example. Let's say that we want to compare -1 to the value of 1. So if we compare RAX to 1, we're comparing -1 to 1, and we know that -1 is less than 1, right? So why don't we do a little test? Let's print out less than, and let's put a print function here real quick. And I'm going to manually call exit here to keep this as simple as possible for this test. So we know that the result of this comparison should be that -1 is less than 1. So if we jump if less than with JL, then we're going to jump to print, and that should print it out. So let's test this and see if it works. We set the value of -1 to RAX. Again, it looks huge. We compare, and now we're going to jump down to print. So you see that this command here, JL, does respect the signed values. It's a signed version of a jump. Now, if we comment this and instead we put jump if below to print, so jump if this number is below this number, and we know that -1 is below 1, but now we're using the unsigned version. So look at what happens here. So we set the value, again, it's a huge, huge value, but it's really -1. We compare it to 1, and we're gonna jump if -1 is below 1. But we don't jump, even though -1 is below 1. And that's because it sees this as a huge, huge number. Even though we put -1 here, we're only setting the bits, but how do we interpret the bits? Well, we do that by choosing what kind of conditional statement we're using. And there's only a few, so we don't need to worry too much. So we have jump if greater than, which is signed, jump if greater. We have jump if greater than or equal to. We have jump if less than, jump if less than or equal to. And these are signed, okay? So we can use negative numbers, they work just fine. And then we have unsigned, where we have jump if above, jump if greater, we could say, or I should put above, I guess. So jump if above, which is greater. So these two are the same. They just treat signed and unsigned numbers differently. So of course, signed works with positive numbers too. It's generally fine to use, but it really depends on your program and what you're doing. So we have jump if above or equal to, greater, again, this is equal to greater than. And then we have jump if below, jump if below, less than, and we have jump if below or equal to, jump if below or equal, and this is also less than. And then we have the regular ones that will work in no matter what. So we have like jump if equal, jump if equal. We have jump if 0 if the result is 0. We have jump if not equal, and we have jump if not 0. And these are the same here. Jump if equal, jump if 0, same exact thing. The CPU sees them the same, and then we have jump if not equal, jump if not 0. These two are also the same. So you could just choose which one you prefer. I think I tend to use jump if equal and jump if not equal instead of jump if 0 and jump if not 0, but I do not think it makes a difference at all. These ones, it doesn't matter if they're signed or unsigned. They're just comparing values. They're not trying to interpret anything in any specific way. But if you are using negative numbers, you're going to use signed. If for sure you're using only positive numbers, then you're going to use the unsigned. But we'll come across this as we proceed into some programs. So don't worry too much about remembering everything here, but it is surprisingly easy to remember once you start using it. So what I think we should do for this challenge is, why don't we build a for loop? So we know in a higher level language, here's a while loop. And a for loop, of course, we have for, and then we have some sort of statement here. Let's say I equals 0. And then we have our condition. Let's say I is less than 10. And then we can perform a statement here, or an expression, some sort of action after each loop iteration. And then we're going to have our body here, and then we have the end of the loop. So why don't we work on this as a challenge? So the for loop is really just a while loop with some features added onto it. So why don't we give that a shot? What we're expecting is for I to be 0 in the beginning, and then after the loop is done, we want I to be 10. So we of course know that we're going to use jump, we're going to use compare, and we're going to initialize. So let's give that a shot. You can pause the video and then I'll proceed into it. So if we analyze this for loop, then we know a few different things. Before we ever get into any of the loops, we need to initialize something. So in this case, we can move rex 0, which we already had. That takes care of this statement. Then it's going to check the condition. So anytime we know we're checking a condition, we know that we have a comparison to make. So we're going to compare, in this case, rex to 10. If it's less than 10, we want to proceed into the body. But if it's greater than or equal to 10, then we want to get out of it. So we can jump if greater than or equal to, let's say, to the exit statement. And then if this fails, right, we fall through to the actual body, which in this case, it's empty, which is an increment, which is right here. So we know that any code here just goes inside the body, and it's just the last line of code that's executed. In our case, it's the only line of code. So we're going to increment rex, and then all we're going to do is we're going to jump to this comparison line. So I guess we can give it a label. Let's just call it maybe compare, and we'll put compare here, and this should work. So let's copy this and paste it here, remove our comments, and see if this works. So we have 0 rex, we're comparing. Seems to be working so far. It keeps looping, 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 jumping. And then finally, when we reach 10, after our final increment here, we jump down to exit and exit the program. We no longer increment, so we end at 10, which was a value of A. If we do it one more time, our interrupt is still here, so we could just click continue. And we see that when that for loop has been exited, when we're finally in exit, the value is A, which is 10 in hex. So that worked out. Now let's look at a compound condition. So what if we had something like if x is greater than 3 and x is less than, let's say, 5. Well, I guess that just means is it 4. So let's say if x is greater than 1 and less than 5, then we want to do something, right? And if not, then we want to exit. Well, all this is two comparisons back to back. And you could try it as a challenge if you want to do this sort of compound condition. Now, our version of do something, let's just say it's to print, and we're going to say do something if it's above 1 and less than 5. So let's say the value of 3. So let's move to rex, let's say the value of 3. And then we want to compare, is it greater than 1 and is it less than 5? So the way we do this is we have all of the conditions laid out. So we have compare rex, and we know we're comparing it to 1. And then we also know that we're comparing it to 5. I'm just writing them out. We do need to make jumps in between, because any back-to-back comparisons will clobber the first one's result. So we do need to compare and then use that value right away to make sure that the flag registers don't get changed by anything else. I'm just writing them so we can see that it's two conditions back-to-back. So in this case, we want to check if rex is greater than 1. With an if statement, if this is false, we jump to the end. If this is false, we jump to the end. Only if both are true do we fall through. So that's easy enough to do here. We're going to jump if less than or equal to, and we'll jump to exit, right? So the statement here is if x is greater than 1. That means that if x is 1 or less than 1, then we fail and we exit the if statement. That's what we do here. If rex is less than or equal to 1, in other words, it's not greater than 1, we jump to exit. But if it is greater than 1, we go to the next comparison and we do the same thing. We're comparing if rex is less than 5, right? So if it's less than 5, we want to fall through. That means that if it's greater than or equal to 5, we want to skip to the end. So we'll do if jump if greater than or equal to, and we'll jump to skip. So jump if greater than or equal to exit. So let's compare this and check it. We know that we set it to 3, and we're going to compare it to 1 to start. It seems to pass that test because no jump occurred. And then we compare it to 5. So what we want to do is have our jump to print here, which would be our do something. Say we have print here. So the only way it will reach print is if it passes these tests. It will jump away if it fails. And the fall through, this will be the body of our if statement here. So we go through, it passes all the tests it seems. And then we get to our body here, jump 17, right? So we have our conditions. So this is just our double condition here, our compound condition. If this and this, and then we have our body, we step through, we go to print, and it does say do something, and then we jump up to exit, and we exit the program. So for a compound AND statement, we're going to jump away if any of them fail, jump to the end. What about for a compound OR? So if we have x is 0 or x is greater than, let's say, 50. So if it's 0 or it's greater than 50, then we'll perform our print. So this one's going to be a little bit different because with the AND, we're jumping away if we fail. But with the OR, we really want to jump to the success on any condition that passes. So in this case, we're going to, let's say, set the value to 0, and we're going to compare it, right, to, what was it? To 0 itself. And we're also going to compare it to 50. So we have our print here. So all we want to do is we want to jump if they're equal, right? So this one writes itself a little bit better, logically speaking. So jump if equal to print, because we want to check first if x is 0. So jump if these two are equal, if x is 0. If it fails, we still check the next condition, right? Because it's an OR statement, either this one or this one. So let's compare it to REX, and we want to jump if greater than, right, to print. I think that's what we had here. Jump if greater than 50. And then in this case, if these fail, then we just fall into the failure. And we can configure this in different ways, but this is the way that comes naturally to me, at least for this example. So if we compare it to 0, we know that it is 0, so we're going to jump all the way down to print. We don't even have to consider this condition. That's of course how the OR statements work. The first one passed, so we do go down to print. Now let's say that REX is the value of 3. So we compare it to 0, but this one fails, so it doesn't jump. So now we move to the next comparison, and we see, is it greater than 50? This one also fails. So we fall through to exit, and we just crash out without printing anything. If we turn this now to, let's say, 99, then we know the first condition is going to fail. We fall through. Second condition, however, will pass, so we jump down to print, and we print it out. So any kind of compound conditions, multiple conditions together, are just going to be sequences of comparisons. And you sort of weave the logic into conditional jumps based on the combination of what's happening. So if you have an OR statement, then you're going to consider every single one until you have a success. Then you're going to stop and you're going to jump. If you're looking at an AND statement, then you're going to jump to failure as soon as one of them fails, because of the way, of course, the AND statement works and the way that the OR statement works. So these are conditional jumps. I hope this is helpful, and now we're finally able to build real programs that do helpful things and real things that all of our libraries have. For example, the first one that we're going to do is the string length, because right now we have to calculate the string length at assembly time. This is sort of an assembly time, like macro replacement that sort of happens here, to borrow a phrase from C, where this is actually going to be replaced in the binaries. This isn't going to be calculated at runtime, but of course, the vast majority of times we're going to have strings at runtime that we don't know what they are, and we need to calculate the length. So that's what we're going to do in the next video. We're going to be able to simulate getting input from something that we don't know the length for and still pass it to print and print it out, because without this length here, it won't print anything. So we're going to build our string length program where we can count how long a string is and pass it into print as an argument and print out strings, much in the way that all of our programs at some point have to do when we enter anything into a terminal or get a packet on the network or anything like that. We do need to count the number of bytes, the number of characters in a sequence or a string of bytes. So that's going to be the first up on our list. So that should be fun and exciting, and we're finally going to make something that's useful. So that's a cool sort of milestone for us to reach. So thanks very much for joining me. This has been fun, and I will see you soon.